Hello everybody. Today I would like to talk about differentials and specifically using differentials to approximate function values. Alright, so basically how we do that is by using a tangent line to approximate the function values. Alright, so as you can see I have my graph here and I've got some math up here. Now, I'm just going to explain the graph a little bit. Well, this purple function is the function that we want to approximate, and as you can see, it's a square root function. It's y is equal to square root of x, because I think that's the most common function value to approximate a square root function. So I've got my purple function here. I've got my tangent line. Now, so basically on this graph we have 2 points here. I'm not sure if you can see these points, but we have this point here and this point here on the graph itself. Now, basically this point here and this value on the x represents a function value that we want to approximate, that's hard to approximate. Let's say like the square root of 30, something like that. Let's say now that's what that represents. So this point here, this value represents an easier function value that we know how to calculate. So now we want to see what the difference between our real the function value, the actual function value, and the function value we chose that's easier. So as you can see, that difference is delta y, the actual change in the y, or the height of the function. So now we have c, we went out c units to the right, and so this point is c and f of c, and so from c we went delta x units out more. So now that's c plus delta x, which is this point. So this point I didn't get to write it here because I didn't have space, but it's c plus delta x, f of c plus delta x. So of course this height here is f of c, as I marked here, and this height here is f of c plus delta x. Now, like I said, we want to find this delta y, the actual change in y. That's what we're trying to find, but we're going to have to settle for an approximation in most cases, and that's what we're doing here. So now, what is the actual change in y? Well, graphically, if you see this height here, this f of c plus delta x, if you subtract from it f of c, then that leaves you with delta y. So I have here, and I color coded it, that delta y is equal to f of c plus delta x minus f of c. So that's this part minus this little part, which leaves you that part. Now all of this is approximately equal to f prime of c times delta x. So that's what we're actually trying to use as the approximation. So in this case, like I said before, we're going to have a value here on the x, and we're trying to find what the y value corresponding to that x value is. So we make an approximation by using the tangent line. So we're going to actually get a value that's on the tangent line, that's close to that point, and so the difference between the tangent line value and the actual value will be our approximation. Alright, so now if you add f of c to both sides, this gives you that f of c plus delta x is approximately equal to f prime of c times delta x plus f of c. Now graphically you can see that too. This height here is approximately equal to this plus this. So if I had this, and let's say take this here, this part f prime of c times delta x, and I put it here. See, I'm not sure if you can tell, but my index finger isn't reaching all the way to the actual height. It's not touching the graph, so it's just an approximation. This f of c height plus f prime of c times delta x. That's just, that's very close to the actual height, but it's not the actual height. So as you can see, this value here, this actual height, is approximately equal to f of c plus f prime of c times delta x. So graphically you can see it here, and the math checks out here. So now, since we're using tangent lines to, or tan lines as I like to call them, uh, since we're using those to approximate the function values, pretty much we have to use, well, we don't have to, but I'm going to illustrate the point with the equation of the tangent line, so that I can show you that that this will actually be approximated. I showed you graphically that this delta y and this height here, the actual height, is approximated by f of c plus f prime of c times delta x. But mathematically, I would like to show you. Basically, I showed you that here, but let me show you a little more concretely. So, this tangent line is a straight line. So now we can use point slope form. So we can have y minus y1, which is f of c, is equal to m, or the slope, which is f prime of c times x minus x1. x1 is c. And I use c and I use x. C represents just the value we choose. That's easier to evaluate, and x and delta x is a distance, but x would be the value that we're trying to approximate, and c is the easier value that we can evaluate, and the distance between those two values is delta x. So now x minus c, this is just basically delta x, because we don't care about what happens on the left of this function here. We just care about from this value and on. So we care about basically just the distance between here. So x minus c is always just going to be whatever the value is. So we can just say that this is delta x. Okay. So now, if we add to both sides f of c, this is the equation of the tangent line, and as you can see, it coincides. Okay. So this mathematically, like I showed you in a not very rigorous way, but a little bit more rigorous than graphically. But you can see graphically how that works, how it's approximately equal, and then how they're approximately equal mathematically with these equations. Okay, so alright, so like I said, this value here represents the value we're trying to approximate, that it's hard to approximate, and then this c value is the value that we find easier to calculate. So we base that off of, we base our approximation off that. So we take the derivative of the function, of this purple function here in this case, we take the derivative of the function and find the slope at the easy point that we know how to evaluate. So when we find that, now it's just the height is just the distance between the 2 points multiplied by the slope, which is just like in regular, like in algebra, when you have like y is equal to mx plus b, m is the slope times the x value. It's the same exact thing, plus b. So the b value is the y-intercept, so that's where it starts. So the b value here would be f of c, that's where it starts. And then the slope multiplied by the x value in y is equal to mx plus b will give you the y value, and the same thing here, the slope multiplied by the x value. It's all the same thing. If you think about it that way, I think it's a little bit easier to realize. So now, as you can see, check it out graphically. The smaller the delta x value, or the smaller between the smaller the magnitude of the distance between the value we want to approximate and the easier value c, the smaller that distance is, the better the approximation. As you can see here, we have delta x this large graphically, so that corresponds to a relatively small disparity between uh, the approximate value on the tangent line that we're going to calculate and the actual value on the graph. Now imagine if we had a larger delta x. Imagine if the point that we wanted to approximate was out here. So delta x would be, instead of that small, it will be this large. So we have this as our point that we want to approximate, and we choose this point as the easier value. So we have a large delta x, and subsequently we're going to calculate our approximate value on the tangent line up here. It's even off the board. So then the distance between our approximate value and the actual value is very large. So you can see how as delta x gets larger and larger, the approximations get worse and worse. So basically you just want to always choose the smallest delta x as possible. Alright, so let's try and do an example. So we're going to do the example of the square root of 27, because I want to show you that with a very small delta x, you get a really good approximation. Alright, so this is actually the form of the differential equation. Not differential equation, I shouldn't say that because you might get confused with differential equations. The actual topic. No, the differential formula, I should say. Okay, so we have f prime of c times delta x plus f of c. So these c's, of course, are the easier value that we use to approximate this function value. Now, when you're actually doing it, you're not going to, you may or may not, most likely you're not going to use c, but you'll use x's. So I'll use c here just so that I can show you on the graph while I'm doing the calculation. So now we're trying to find the differential. So y, well, yeah, y is equal to f of c. Well, actually, let me erase this part here so I have space. Okay, so y is equal to f of c is equal to the square root of c. So we're trying to find the square root. Since we're trying to approximate a square root value with this graph here, we have y is equal to f of c is equal to square root of c. Okay, so now our actual value, we're going to say, we can say c plus delta x is equal to 27. This is the value that we're trying to approximate, like I said before. We try to find this y value that corresponds to this value here, and this value is 27, so on the 27 as x. When you're actually doing differentials, you're not going to write c plus delta x, you're just going to say that x is equal to 27. But, like I said, so that I can show you on the graph, I'm going to write out with the notation that I have on the graph. So, that's 27, this is the value we want to approximate, and so c is equal to 25. Alright? So this is the easier value, because we can calculate the value of, well, the y component of the square root of 25, which is 5. We can calculate that easily, so that's fine. So now, even if you plug in 25 here, you can see that delta x would be 2. So if you just plug that into there, so delta x is equal to 2. So the distance between the value we want to approximate and the easier value is just 2. So it's a very small delta x. Okay, so now we have to find, basically we have everything except for f prime of c. So we need to find that. So we have f of c, we have to take f prime of c. So we take the derivative of both sides. So that's going to be that f prime of c is equal to 1 divided by 2 times the square root of c. Okay, so that's the derivative of this function here. So now let's put it all together. So we're going to say that f of c, I erased the differential formula that I had down there, but this is basically it. If you just add f of c here to both sides, then it's just that part. So f of c, which was the square root of c, which is 25. So we have square root of 25. And then remember it's plus f prime of c times delta x. So plus this part here with c plugged in there, which is 25. So 1 divided by 2 times the square root of 25 multiplied by dx, or delta x. Sorry, well, dx delta x, you can say either one. They're both just a very small value of x, or a very small change in x. So now we can do this part here. So, well, square root of 25 is 5, as we know. Just draw a line there. 5 plus, now we can just cancel out these 2's here, and then the square root of 25 is 5, so that's 1/5. Well, this is all approximately equal to the square root of 27, so let me write an approximate sign there. So now 5 plus 1/5 is 26 divided by 5. And that is approximately equal to 5.2. Okay? So if you actually check in the calculator the square root of 27, well, this is approximately equal to the square root of 27. If you check what the square root of 27 is, you'll get like 5.189 or something, or 5.198, something like that. But it's a very, very extremely close approximation, 5.2. So as you could imagine, if instead of delta x as 2, we had delta x as 10, so imagine what that would have been. That would have been an extremely poor approximation. So as you can see, small delta x, good approximation. Alright, so I hope that this helped, and hope I didn't confuse anyone. So if I did, then you can just leave me questions in the comments section, and I'll be happy to clear things up. And if you need more examples, then leave me questions about that also. Alright, thanks for watching, and I'll see you in the next video.